So with this unit, we talked about what are known as permutations, combinations, and extend into the binomial theorem. So permutation is kind of the basic idea. Combinations are essentially a special type of permutation. Binomial theorem is just using that. Yeah, there's things that we really need to be careful with. But the biggest thing is that, yeah, there's the two aspects. One, talking about permutations, and then the extension of combinations to that binomial theorem. Obviously, we talk about what that is. But first things first, we're going to talk about what are permutations. So permutation is a set of objects where a set order is required, or in other words, order matters. Saying that if I do thing A and then I do thing B, it's not going to be the same thing as if I do thing B and then thing A. An example of that would be like the weird people who put a sock on, then a shoe on, then a sock on, then a shoe on. It's very different than sock, sock, shoe, shoe. Now, obviously, same outcome. So that's actually technically a combination, but again, we're just saying that if the order actually matters, because if you're putting sock, sock, shoe, shoe, you are sane, and if you're going sock, shoe, sock, sock, shoe, you are probably insane. Again, I'm joking, obviously. The second definition is factorial, which is actually this exclamation point. You can actually access an exclamation point using your calculator. If you press the PRB button, so I'm just clicking that right now, you see an NPR, NCR, and the exclamation point. So for example, if I were to type in 5 exclamation point, so I type in 5, press my PRB, I scroll over, use my arrows, click on my exclamation point, it would actually equal 120. Because 5 exclamation point just means that we're going to take descending consecutive natural numbers and we're going to multiply them together. So 5 times 4 times 3 times 2 times 1. If it was just something like 3 factorial, it'd be 3 times 2 times 1, which is 6. We could take any number, but as long as they're natural. So natural numbers are counting numbers, so meaning we can't take negatives. And we also can't take things like, obviously 0. We also can't take decimals. Now, with variables, what that would mean is like n plus 1. Well, if it's n plus 1 factorial, that means that we're going to take n plus 1 and then take one number less than it. So if we take away 1 from n plus 1, we're left with n. If we take away 1 from n, we're left with n subtract 1. If we take away 1 more from n subtract 1, we get n subtract 2. So on and so forth until we get down to 3 times 2 times 1. And this is that idea behind factorial notation. Now we go a little bit more in depth in a little bit of this in Foundations 30, but it's just kind of a fun little bit. Well, I think we have some examples that will deal with this, but we'll get to that when we get to it. Now, some fun facts. First bit is that a double factorial actually means we take 6 and we actually skip numbers. So 6 times 4 times 2. But 6 factorial means factorial means that we still have to do the bracket first. So 6 factorial is actually 720. And 720 factorial would mean 720 times 719 times 718 all the way down to 3 times 2 times 1. So very different notation. Again, this is just a fun fact. Obviously, you don't have to remember that. But it's very, interesting because it's a little bit different. Now, in the same line, if it was triple factorial, we would actually skip 3. to do the next number. And that's just how this little bit of notation works. Okay. So now we have a few specific types of concepts behind here. The first one is the fundamental counting principle. So what this is having distinguishable types of objects, and you multiply the amount of options that are available. So, for example, how many different outfits can Michael wear if he has a choice between 6 shirts, 4 hair clips, 3 pairs of pants, and 5 shoes? How would this look like as a tree diagram? Well, a simple way is just 6 times 4 times 3 times 5. If I hit that in my calculator, there'll be 360 different outfits. Because what these are, and this is how I usually like setting it up, is I just have so many different options. Each of these are options. So this first spot is the options for the shirt. The second one is the option for the hair clip. The third option is the options for the pants. The fourth spot here is how many options do we have for the shoes. Because if we look at it, we could have this look like a tree diagram. Now, this one is a very convoluted one. There's easier ones, especially ones I like doing in Foundations 30. But we could have shirt 1, shirt 2, shirt 3, shirt 4, shirt 5, and shirt 6. All of these are different types of shirts. One could be blue, one could have stripes, one could have polka dots, whatever. But as soon as Michael picks one of these shirts, he still has 4 options for a hair clip. Hair clip 1, hair clip 2, hair clip 3, hair clip 4. But each of these have that option. Hair clip 3, I'll just put H. Yeah. Each and every single one of these have 4 hair clip options. After that, each of these hair clips have 3 options for pants. Pant 1, pant 2, pant 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Every single one of these options have that idea. And we can continue that to the shoes. So 5 different pairs of shoes for each of these pants. Shoe, 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 shoe. 5. 1, 2, 3, 4, 5. By the end of this very bottom row, would actually have 360 different paths that could happen. Because as soon as you pick shirt 2 or shirt 3, you get to choose hair clip 4, and then pant number 1, and then the second pair of shoes. That's one option, but there's a whole bunch of them. And that's what this fundamental counting principle is. We're just multiplying the options. This is what the tree diagram would look like. If I were to ask you to do a tree diagram, it would be one that would be much less convoluted. So let's look at this. How many 4-digit numbers can be formed using digits 1, 3, 4, 5, 6, 7, 8? If the digits can't be repeated. Or what about if it has to be an odd number? So this actually has 2 questions in it. So no repeat. And what about if it has to be an odd number? So again, we're looking at a 4-digit number, and we're looking at how many options we have. So a 4-digit number, still, both cases are 4-digit numbers, so I'm just going to write this black line first. Okay, four-digit number. The first case is the digits can't be repeated. Well, how many digits are there here? 1, 2, 3, 4, 5, 6, 7. So if I just can't repeat any of them, I would have seven options for that first spot. This is not the number 7, even though the number 7 is on here. This is saying that we have 7 options. If there can't be any repeat, say we use the number 4. Well, how many options do we have left? 6. If I use the number 8, then I have 1, 2, 3, 4, 5 left. And likewise, 4. So 7 times 6 times 5 times 4 is 840. There are 840 four-digit numbers that only use the numbers 1, 3, 4, 5, 6, 7, 8. And they don't have any duplicate digits. So how about if we change the question? What if it has to be an odd number? Well, what makes an odd number? That's right. The last digit has to be odd. How many odd options do we have? 1, 2, 3, 4. So this is the key part. We actually have to start at the back here. After this, now, since we're continuing on from this question, let's also assume that it's an odd number and we also don't have a repeat. So as soon as we use one of these odd numbers, say we use the number 3, how many options do we have left? 1, 2, 3, 4, 5, 6. We have 6 options here. Of course, I could put the 6 here or here. It doesn't really matter, but if I use the number 4, then I have 1, 2, 3, 4, 5 options left. And then it actually goes to 4. So 6 times 5 times 4 times 4 is 480. There are 480 four-digit numbers that are odd where we do not have any repetition of digits. So one example could be, let's see, we'll use 3 in the last spot. 8473 is one of those four-digit numbers that's odd. We don't have any repetition of digits. So if that's not fully clear, I'm just saying like 8443 wouldn't fit this can't be repeated criteria. All right. Now let's look at what the permutation formal definition. So permutation is, again, that idea where order matters. And in this case, these orders matter. You do this, then this, then this. So permutation is having n amount of objects that are distinguishable, like the numbers 1, 3, 4, 5, 6, 7, 8. But only being able to take r amount of them at a time. That's the NPR. And once again, you can get that NPR by pressing that PRB button. The n, so the number of distinguishable objects, factorial, divided by, so again, remember that definition of factorial is just the descending consecutive natural numbers that you multiply together, over n subtracting r factorial. It can also be evaluated using a calculator. So what we're going to do first is we're going to use some pre-calculus methods, NP or NP2. So this one, n is actually n. So we're going to put n, sorry, if you hear there's a little bit of rattling with my table today. If you hear that, I apologize. But n factorial, the n is just going for the n. So n, the r value, so this r value is 2 in this case. And that's going to equal 56. So what we're going to have to do first here is we're going to have to solve. Now, yes, we can do guess check, but that's not using our pre-calculus methods. And then we're going to actually verify our answer in this next example. What we're going to do is we're going to simplify. In order to simplify, we use this definition of what a factorial is. Again, it's descending consecutive natural numbers. Well, we don't exactly know what n is right now. I mean, I do, but that's beside the point. If we use variables like n plus 1 factorial, we're just going to take each number that's 1 less than it. So n plus 1, then n minus 1, then n minus 2, n minus 3, n minus 4, all the way down to 3, 2, 1. Generally, the easiest way is choose the biggest. Choose the biggest variable. Between n factorial and n subtract 2 factorial, n is bigger. So if we're going to start with n, we're going to multiply it by what's one number less than n. We're just going to subtract 1 from it, so it'll just be n subtract 1. And let's go further. Now, we could technically end this here. And this will be all over. Now, don't write this factorial, because you're going to have to erase it. But it'll be all over the n subtracting. Sorry, I'm just going to leave that as, I like leaving this as blue just so you can see that. We can leave it here, but we need to erase. We need to still get further because we actually have to do this simplification. In order to simplify this, what's 1 more less than n subtract 1? N subtract 2. And we're going to put a factorial there. Because it's still every single number that's less than this. Now what you should hopefully see here is we can cancel things off. We're going to take off this n subtract 2 factorial and this n subtract 2 factorial, just like our rational expressions. So we would be left with n and n subtract 1 equals 56. So then we essentially go back to pre-calc 20. Let's distribute, give one side equals 0, and we'll factor. N times n is n squared. N times negative 1 is negative n. That equals 56. Of course, I'm going to subtract 56 over. And bring my work on up here. So n squared, subtract n, subtract 56 equals 0. Find out our P&S, or product and sum. A product of negative 56 and a sum of negative 1 is going to be negative 8 and positive 7. Now, I don't have to worry about anything further because we only have a 1 in front of our n squared. So we are just going to plug those numbers straight in. Of course, if we had a number in front of that n, or that n squared, then we'd have to get rid of it, or we'd have to do a complex factoring. But we're just going to plug our negative 8 in and our positive 7. And subtract 8 and add 7. Where do these values equal 0? Well, this would be n equals 8 and this will be n equals -7. So we have two answers, right? Hopefully you know by my tone. No. N is this, N is this, N is this. With a factorial. Something like an n factorial. Now with that n factorial, this n factorial, factorials has to have descending consecutive natural numbers. One of these numbers is not natural. One of these things is not like the other. -7 is not a natural number, it's an integer, which means we only have one answer, and it's 8. There might be some situations where we will have two answers. Actually, we will have some answers with combinations, but we'll deal with that when we get combinations. This is still permutations. So we only have one answer. Now we can solve this by the factorial, and it doesn't hurt to know what that is. If n factorial is 8 factorial, and 8 subtract 2 factorial, well, let's start this off. 8 factorial, 8 subtract 2 factorial, 6 factorial. 8 factorial is what? 8 times 7 times 6 factorial. Now I could continue this on as 6, 5, 4, 3, 2, 1, but it would be a little bit redundant just for the fact that this is already 6 factorial. So again, what I could say is I could write this as 8, 7, 6, 5, 4, 3, 2, 1, but then I'd be doing the same thing on the bottom. 6, 5, 4, 3, 2, 1. And then I can do a whole bunch of canceling. 6s, 5s, 4s, 3s, 2s, 1s. Or if I leave it here, 6 factorial, 8 times 7 is 56, which is exactly what my question is. But if I want to verify using my calculator, what I need to do is I need to use that PRB button. So we're just going to check that 8 actually works. So what you need to do is you need to type in the number 8, press the PRB button, so 8 PRB. Now, NPR is actually the very first option that shows up. So you can just press enter. You could actually also just immediately press the number 2. So you can press enter or the number 2. And what that does is what you will see in your calculators, you'll see 8 NPR2, but what that does is it just puts the 8 in for the N and the 2 in for the R. Either way, you press equals, and you get the answer of 56. So yes, you could guess and check, but when I say using the definition is, I'm asking you to use this. Because really, the word for it isn't that hard, especially since we know how to do that factor. The only hard part is just starting with that biggest number and just take it down. Right. Next example. How many 4-letter arrangements can be made using the different letters from the word Steinhubel? Well, there's 2 ways of doing this. We need a 4-letter arrangement. How many options do we have for the first? Well, we have 9 different letters here. Again, these are options. 9, 8, 7, 6. So 9 times 8 times 7 times 6 is 3024. But that's not the only way that this can be done. Because what this permutation is, where that order really does matter. So again, this four-letter arrangement using different letters is just that idea that STEH is not the same as using HTSE. So still using the same letters, but the order being different and it not matter, or when it does matter, is dealing with that permutation. So again, let's go back to another definition. More specifically, the permutation formal definition. If we have n amount of distinguishable objects, and we take r amount of them at a time, we can use this NPR. We have 9 distinguishable objects. We have 9 different letters. We are taking 4 of them. Now, as long as we don't have any repetition here, we're set. We have 9 objects, taking 4 at a time. If you type that into your calculator, so again, that you press the 9, then you press the PRB button, PRB, and then the 4. Oh, calculator. There we go. We still get 3024. So either we do it by the fundamental counting principle, or that idea that if there's no repetition allowed, we can use this formal definition of a permutation. Now, how about if we had to change this question to be how many arrangements of 6 or more letters can be made? Well, that's actually pretty easy. How many ways can we use 6 letters? Well, that's just going to be NP6, which is 60,480. This or more part is just saying we can use 7, which is 181,440. So again, if you choose 7 random letters here, there's 181,440 different ways that you could put them in orders. Again, where the order actually matters. How about NP8? That is 362,880. And notice how it's increasing. Now, here's actually the fun bit, is 9P9 is also 362,880. Now, I'll explain this in a second as to why. But how many arrangements? All we're going to do is add up all of these different options. So if I take all of these, add together, I get 967,680. So there are almost a million different ways of just choosing 6 or more letters from soluble, putting them in some kind of arrangement, and them being completely different. So yeah, that's that question. We'll use this a few times. Now, I just want to explain this part. Again, let's go back. Let's understand that definition of what a permutation is. N factorial over n subtracting r factorial. So if we use this, what this is saying is that 9 factorial, so let's use this 9p8, 9 factorial, 9 subtracting 8 factorial. That has to be the exact same thing as if we took 9 factorial over 9 subtracting 9 factorial. So can't simplify the numerator at all. 9 factorial, 9 subtract 8 is 1 factorial. 9 factorial over 0 factorial. Well, you'll notice that both numerators are 9 factorial. 1 factorial just equals 1. So 9 factorial divided by 1 is going to be 362,880. But 0 factorial also equals 1. It's very counterintuitive. At this point in time, I can't even remember the exact explanation, but it's you can actually type in 0 factorial. Again, you press 0, the NPR, scroll over to your factorial, press equals. It does equal 1. It's not an error. You're not actually dividing by 0. You're dividing by 0 factorial, which is a very weird way of doing this. Yeah, I'll have to search up the explanation. Of course, you could Google at any point in time as well. Just why is 0 factorial 1? You'll very likely find a lot of explanations. I'm just glad that Siri didn't catch that question. Still didn't, which is good. Yeah, I will try and find the answer, and I'll explain when I have a chance. Okay. Example 7. How many different orders might 15 runners finish a 10-kilometer race? Long story short, how long the race is doesn't matter. It could be a 1-meter sprint. But here's the idea. How many ways can someone come in first? There are 15 different runners, so there's 15 different possibilities for gold. Obviously, training and all that stuff comes into effect, but we're just saying if everyone has a fair chance, there's 15 different ways that gold could be awarded. If gold is already awarded, there's 14 ways for the second one, for silver. There's 13 ways for bronze. There's 12 ways for the non-contender. On and on, all the way to 3 times 2 times 1 for the last place. This is the same as 15 factorial. It's also the exact same as 15p15. I don't think I already said it, but P stands for permutation, if that's not obvious. So I can type that in. 15, and I could use any explanation. I could write 15 times 14. I'll do all those. I could do 15 factorial. I'm actually going to choose this one because it's just shorter to do. Or I could type 15p15. I get the exact same answer of 1.31 times 10 to the power of 12. So let's see, that works out as 1 hundreds, thousands, millions, billions. That's 1,307,674,368,000, and we don't know how many hundreds, tens, or ones there are. Of course, if we did it by hand, we could do that. But there's a lot of different ways that 15 runners can finish a race. Okay. So we've done what the fundamental counting principle is. We're just having the options. We are talking about this language bit. This language bit is going to be one of those key aspects. Are you repeating decimals or repeating digits or letters? Hopefully you know how many letters are in the alphabet, which is a really common question. 26. Hopefully you also know what vowels and consonants are. Vowels, A, E, I, O, or U. Constants are the other 21. What even and odd numbers are. What the formal definition of permutation is. And that's that NPR, that idea of having so many or more. And the last bit is repeating objects. Now here's one other formula. Yes, this is actually a formula. I mean, so is So is this technically. It's a definition, but it is a formula. If I set a number of objects have identical object elements, I need to fill the rest of the definition. Basically, n is the amount of total objects that A, B, and C are how many times something is repeated. So for example, the 5-digit number 17171, 17,171, has 5 total digits. The number 1 repeats 3 times, and the number 7 repeats 2 times. If you're going to type this into your calculator, please put this in your denominator in brackets. But of course, whenever possible, I like showing things just with this factorial, just so you understand further what it is. 5 factorial is 5 times 4 times 3 times 2 times 1. But I say that 3 factorial because I know that in my denominator here, I'm going to be able to cancel this 3 factorial with this 3 factorial. But what about this 2 factorial? Well, the 2 factorial is just 2 times 1. But I can reduce this. 2 and 4. I'm left with a 2. Dividing by 1 doesn't change anything. 5 times 2 is 10. If you type this in your calculator, you're going to get the exact same number. So there's 10 different ways that we can write this. As an exercise, you might want to actually write this. This is one way. I'm putting all the 1s first, the 7s first, switching them up, doing all that. Those are all different ways that it matters, because as soon as you change the location of this 7 or this 1, you have a different number. But there's only 10 that are possible. Right. Now, in all technicality, this is actually a very good thinking question. It's usually done as a spatial game, spatial understanding as part of kind of the workplace. It's also technically, again, in all technicality is also combination, but we'll talk about combinations in the next section. It is a repeating object because we have to go from A to B, and we have a certain amount of ways that we can do it. We can only go down and to the right. Well, if we count it up, we have to walk 5 blocks to the right and 3 blocks down. No matter which way you go, that's a total of 8 blocks. Divided by 5 of them being to the right and 3 of them going down. So once again, I like using the definition of what factorial is. Just instead of me having to type everything in my calculator, I'm not going to stop you from using a calculator. I just like doing it this way. It's just kind of a habit of mine. 5 factorial, I know that that's going to cancel off. 3 factorial, well, nothing really here that I can really fully cancel, but I know that 3 factorial is 3 times 2 times 1. 3 and 2 is 6. So divided by 1, 8 times 7, 56. Okay, rock and roll, and have some fun.